So here we're starting off with networking week. Here's a who am I slide of me. I'm a third year CIS student and I work as a information system security engineer. Dang, your AirPods don't work. I'm the captain for this year's CCDC team. I was networking for last year as well as like a virtualization admin, and then I was a Windows lead for the year before. And I've been a CPTC moral supporter since I started at the school, but I'm not an actual member. That's too hard.
My name is Marshall. I'm a third-year
Mung.
computer engineer. Yes, Mung. For CCDC, I'm the threat hunter currently. I was the alternate threat hunter last year. And of course, for CPTC, I'm a team member. Alternate last year as well.
Hey guys, my name is Jess. I am currently the CCDC business lead, and I was on the Windows team with Evan before. And I'm also the co-president at Swift, and I'm currently a pentest intern at Visa.
So today we're going to just be going over the networking that is involved in the competitions like this, as well as some firewalls and intrusion detection and prevention that will probably help you during future jobs if you're going into cybersecurity or, this tryout / bootcamp as well. So Mung, take it away.
All right, so first we'll be starting off with intro to networking. So what we have here is a quite basic network topology, which is just a diagram of all the network devices on your current network. We have a bunch of different things like servers on this network, switches, routers to route everything, switches to connect the end devices together, and a bunch of other things. We'll be going into this a bit more in depth later. I believe, like quite literally next slide. Sorry. So what exactly is a network device? Well, it's anything on the network, as long as it can connect to the network through a network interface card, and of course, with that, it needs to be able to communicate with other devices on that network, then it's considered a network device. Network interface cards can be either wireless, which you commonly see with laptops or cell phones, or wired, which you can use to connect with Ethernet. So we'll be going over some quite important lingo for not only this presentation, but it'll be very important to know throughout the entire bootcamp. First, we'll go with IP address. So an IP address essentially links, it's basically an identifier for a device on a network. Subnet masks, which we'll talk about it more in depth on the next slide, but it essentially tells you what IPs you have on your current IP range. We have a router, which just routes traffic throughout the network. Default gateway. A default gateway is where traffic is sent when the destination doesn't match anything that is currently on the network. So say you're trying to connect to something connected to the internet. Maybe something like youtube.com. That's obviously not going to be on your own home network. So it's going to be sent to your default gateway, which in this case is usually combined with your router. Service. A service, well, it's kind of something running in the background. Not necessarily. It's a task running in a background, and it usually doesn't need to be managed by the user. It's usually invisible to the user unless they're directly checking for it. Though I could be wrong on that one if Evan wants to clarify.
Yeah, for this I was just gonna say like service is a application running typically on a server and it's providing a service, right? So like a web server is providing the web service, and then your users will interact with that service and get their web pages.
Yeah.
And then, yeah.
And then a protocol is the set of rules that define how the communication will actually occur. So we'll be going over, in this presentation at least, TCP and UDP as network protocols. They're different ways that network is sent to other devices or throughout the internet. We have ports, which is how you can actually interact with other it's how you interact with services on other devices. That sounds not the greatest. If Evan wants to chime in.
It's like where you have your IP address, which is identifying a specific computer or network interface card. You have your port, which is identifying a specific service that's running or being shown to the public on that network interface card. So it's like if you were a child and you asked your mom, like, hey, I want to go to my friend's house, and your mom would know your friend's address. So that would be the IP address, like the home address. And you get there, you get to the default gateway, which is your friend's mom. And she's like, oh, you're looking for your friend? I know where her room is. And that room would be like the port. And so that combination of the house address and a port is like a identifier for how you can access that service, which in this case would be your friend's room.
Yeah. Interface is how a device actually interacts with other devices on the network, and a firewall mediates the traffic between either the devices or throughout the network, depending on if it's host-based or network-based. So as I talked about before, we'll be talking about what a subnet mask exactly is. There's some math involved to figure out what IPs you have on your current IP range. If you were to convert the 255 into binary, you'd be able to easily tell. But as I said before, a subnet mask defines what IPs are on your current range. And it's broken down into two different types of notation. I can't remember exactly what the current notation is shown on the slides. But there's also CIDR notation. I don't 100% recall what that stands for, but it's a quicker way of showing what IPs you have on your current IP range. Sorry.
Yeah, that's what it is.
Yes.
There's a lot of like binary math. You can drop that. But for now, like the math really isn't important for our use case here. And it's just kind of like, oh, IP ranges typically go from 0 to 256. You can't use 256, so it's just 0 to 255. And if it's 255 in your network mask, that's how you know, okay, this number right here, so like 192, that's a network portion of your IP address. 168 is also a network portion of your IP address. 1 is also a network portion of IP address. And 0, which leaves our last little octet here as our variable in our IP addresses. So like this is what will differentiate your hosts on your network. So like first 3 octets, that's your network portion. Last portion is your host portion. So you can identify your network, identify your host on the network.
Yes. And so now we'll be going into the competition networking. So here is an even more simple topology, though it's a simplified topology of how the competition works. On the left, we can see the blue team subnet. This is where we will actually be trying to fix stuff, and it hosts the services that the core network on the right will attempt to access. And the core network consists of the scoring engine, the red team, the router that actually routes all the traffic, and of course, orange team, who are general users who are trying to access the services we host on our internal network. So this topology is quite simplified, and it actually gets a bit more complicated than that. Specifically, the competition uses natting. One-to-one natting, however, it's important to know what natting is in general and why it's used. So NAT stands for Network Address Translation. And what it is translating private IPs into public IPs. The reason why we're doing this is because IPv4 is quite limited in the total amount of IPs we can actually have. I don't remember the number off the top of my head, but because we only have 4 different octets of 255 each without any like letters, which IPv6 has, we're quite limited on the total amount of IPs we actually have. And as we came closer to that limit, natting was created in order to actually extend that. So as we can see here, we have one-to-many natting. One-to-many natting is what we use to actually extend the amount of private IP or public IPs that we can give out. So on the bottom, we can see on the left side, we have two different servers, and they ultimately link up at the router to form a single public IP that the client can use to interact with. As you can see, we've now saved 2 IPs. We've saved 1 IP by combining the 2 together. Now, one-to-many natting is useful. However, it doesn't have the ability to host multiple different services on the same port. So say we're hosting a web server on like 80 or 443. If we're hosting 5 different web servers and we're trying to connect to that web server using the one public IP, how exactly does the router doesn't exactly know who to send that traffic to, whether it be one of the other, whether it be the actual destination you want or one of the other 4 destinations that are hosting a different service just on the same port. So we can address this with one-to-one natting. And what one-to-one natting is it's directly translating a public IP to a private IP. This is what the competition actually uses. And the benefit of this is that we can have multiple different services on the same port, as we now have multiple different IPs we can actually access.
Yeah, and so in these diagrams, I use the IP ranges that you'll typically have in our environments, in which your private ranges that you'll interact with are 192.168.1s. And then say on the outside of your network, you'll be trying to access your services through a 172.16 dot. And then this would be like your pod number that you see in vSphere, and then dot your host address of your web server. And so get used to this notation. You'll be using it a lot in our homeworks and as well as like tryouts and stuff like that. So let's move on to understanding the client server model. So here's a very like basic diagram that I drew up of the client server model. You have your client, you have your server. This cloud represents just any network that will be in between these 2 clients and servers. It could literally be directly connected. It wouldn't make a difference. But essentially, it works like a restaurant. You're a client. You're trying to order some food from your server. Server serves you some food. You know, that's the typical client-server relationship. It's a very analogous to human client-server relationships. And so the important part of why we mention ports and IP addresses and services is because the client-server model relies on these things to identify what the client is requesting, what the server is serving, things like that. And so here we have like some examples of what port numbers would be, also with their typical protocols. It's like FTP works over TCP and UDP. TCP, I'll explain TCP and UDP later, but it's like it uses port 20 and 21, and then like SSH port 22, etc. you can find like pretty good diagrams online of all the services and port numbers that you could need. And I recommend looking that up if you're trying to do the tryouts and get good at inventorying the network. And so what are TCP and UDP? These are transport protocols, and their general purpose is how can we get the packets to the clients and from the client to the server. And so TCP, this is a slower, still very fast in like human terms, but it's really good at error checking, and it's really good at making sure the data gets there without any errors. And so you have your handshake establishing this connection between the server and the client, and you get synchronization. So this basically just ensures that packets will arrive in the correct order. They'll be error checked. There will be no corrupted data, things like that. Typically, these services will be web pages, kind of small data packets that you need to be accurate. Whereas UDP, fast but unreliable, no error checking, it's just sending stuff out. Like this is what kind of streaming services is, right? Like you have a lot of data in the form of pictures coming in, if you're streaming Netflix. You don't need every single pixel to be picture perfect, That's just going to slow down. You don't want to watch a buffering screen instead of a show. And so here's kind of diagrams of what that looks like. You can see on the left, TCP, it has this handshake right here, establishing the connection between the client and server. And this connection is what gives it its reliability, its error checking, etc. And then on this side, you can see it's just you get a request and you send a lot of things hoping that your receiver gets the packets. There's no guarantee. It just sends goodbye. And so in my previous example of when you're a child from wanting to go to your friend's house, I mentioned that there's a combination of IPs and ports. And so the significance of these combinations, called sockets, in the client-server model is this is how your clients are identifying your servers, and this is how your servers are identifying your clients. So in this example, we have a server at 192.168.1.58, and then the client is 192.168.1.10. So how is the client going to specify what service it wants from the server? Well, it has to use a socket. So here at the bottom, we have examples of the two sockets that would be involved in this connection. On the client side, it has a very high random port number given to it. And on the server side, it has the typical web server port 80 connected on its socket. And so this very high one is a randomly assigned one. This is just so your computer knows, okay, once I receive the packets from the server, what application will I give those packets to? So that's what that port number means. And it's just randomly assigned. They're called ephemeral ports. On the right side, we have port 80. This is consistently going to be there for that server unless the web admin changes the port that it's hosted on. But typically web servers on HTTP, not secure, will be hosted port 80. So the client knows this, it'll request this IP with this port, and then it gets a response from the server. And so why would you need to know about sockets? Well, here's a little command I ran in my terminal showing oh, here's what's being hosted on my device, right? These sockets 0.0.0.0 means that this 135 service can be accessible from any IP address that would be associated with this computer. And then the foreign address is showing what IP is connected to this service right now. And it says 0.0.0.0 because this is just saying, okay, this service is open to anyone. Anyone can access this service. If you see the state is listening, that means that your computer is listening for connections on this service in your local address. So this is very useful for figuring out, okay, what services is my current server hosting? Who's connecting to my services? In the state, it'll say connected, I believe. In Windows, it says connected. Probably says the same thing in Linux. NetStack as well. But this is helpful if you know the IP range of red team, if you know the server, the scoring engine server IP, you can be like, oh, why is red team connected to my service? And you'd be like, I'm going to block that network address, or, just monitoring your network addresses through sockets like this. Yeah, this is just review. These are the important parts. Remember your TCP and UDP, they're different. Networking devices will interact with them differently, so it's important to know and specify which one is which. Ports, there's ports, common ports, you can look that up. Very useful online resources for that. And then just remember, if you see a high port, looks really random, it's probably an ephemeral port on your own computer connections, but it also could be some funky red team activity if they choose a high port. And so to combat that funky red team activity, we can go into firewalls. And right now, there's kind of two branches of firewalls. You have next generation firewalls and then a traditional firewall. And then these list the main differences between the two, and I'll kind of go over them pretty quickly so we can get to the demonstration. But with next generation firewalls, it says stateful inspection, right? So this will monitor the states of your TCP and UDP connections, because some attacks will typically have abnormal states if an attack is occurring. And so firewalls are really good at inspecting those states, figuring out what shouldn't be there, and then blocking traffic based on that. Comprehensive application control. So this is like, oh, someone on my network is trying to use this website, or someone on my network is trying to use SSH. You can just block it based on the application and the network traffic. And then easy to install, configure, integrate security tools. Yeah, you're going to pay more for a nice firewall, so you better be able to easily configure it, Next generation firewalls integrate with a lot of things, a lot of different services. You can like integrate your identity management into your firewalls, so you can see what users are doing what network traffic, things like that. A lot of next generation firewalls, you can decrypt the encrypted traffic going through your network. So like you can do inspection on your encrypted web traffic and things like that. So you can block restricted websites into your network, inspect any encrypted traffic really for malicious / restricted things. And then typically an IDS, so that's intrusion prevention system and intrusion detection system. These are very nice for detecting strange network traffic, malicious network traffic, and then blocking that traffic. So it'd be like exploits going over the network. And then your traditional firewalls, these can do the stateful inspection. So that's like, okay, is this a TCP connection? Did we allow it in? Okay, we can allow it out. If we allowed it in, it's probably good. Yeah, stateful like that. Partial application. So this kind of manifests in Windows firewall, where you can block specific processes or applications from making network connections. And it's not too strong in terms of like the next generation firewall, where you don't need a client on every single host that's making network connections. But whereas in the traditional, your firewall has to be on that device to get the application control. And then, yeah, traditional, it doesn't have any features, so it'll cost more. So if you like manage entirely on Windows firewall, you may have administrative overhead. But for smaller networks, you would go typically with only traditional firewalls. Traditional firewalls cannot decrypt traffic. So you have any encrypted web traffic going through, you're not going to be able to filter that. And then with a traditional firewall setup, you typically have a separate device as acting as an IPS or IDS, or a separate software. And so it's more setup, but less money if you're a small network. So back in the last slide, it mentioned stateful inspection. And here we have the definitions, right? So stateless, it'll literally just look at every packet. Void of any context, it inspects data. Data is bad, it'll drop the packet. Stateful, this is going to look at the entire connection in a whole. So if it marks the connection as secure, it'll allow the whole connection. It doesn't have to inspect every single packet. But it can still do some, say if you have an IDS or IPS integrated into your firewall, it can still do packet inspection on those packets in the firewall, in the stateful connection, and drop those states if it finds a malicious packet. And so an example of this, stateful, which most firewalls will be, is your Windows firewall, right? Say you're allowing web server connections inbound to your web server. You don't have to specifically allow web server connections to go outbound because your stateful firewall sees that, okay, you want it to come inbound, it assumes, okay, you want the traffic to also go outbound. So you have that one rule, inbound, allow port 80 for your web service. No longer needs an outbound connection rule. But if you had stateless, right, you need that inbound 80 rule, and you'd also need a specific outbound port 80 rule so that the firewall knows, okay, allow these port 80 rules outbound. However, you most likely will not have to worry about a stateless firewall, at least in this example. Yeah, and so kind of what I was saying, here's some examples of rules that you may want in an event coming up in the next month. Inbound rules only route your required services. Required subnets, right? Like you don't need to allow a subnet if it's completely malicious and you know it's malicious, right? Just block it. Certain IP addresses. This one a little more dangerous because our scoring engine may or may not change addresses every check, things like that. Also, real world IP addresses change all the time. So blocking, only allowing like 5 IPs, probably a bad idea. Outbound, block everything going outbound. However, you will probably lose access to do anything, right? If you can't talk to anything, you're not going to get anything. So that's just a concern you may have when doing outbound filtering. Very powerful though. So here's some examples on a pfSense firewall. And then this is a rule, right? It's allowing everything from this IP source inbound. And the asterisks mean everything. So like port, any port, destination, any destination. And then here's a LAN firewall, also known as outbound firewall. And again, you can see you can configure it to only allow from your LAN subnet, only allow to your LAN subnet with these ports. You know, very useful rules. You can make it super granular to make it increase security, but less functionality. It's time for a demo. My screen share is going to pause.
Yeah. Just
Let me get this set up real quick. All right. So in this demo, I'm gonna be trying. I don't, to be honest, I don't know if the demo works right now, but I have a intrusion detection and prevention system set up on this pfSense, and then I have a vulnerable window file that I'm gonna try to exploit. There's so many tabs. Right. So my vulnerable Windows box is like a server 2012 FTP server with SMB running on it. And one of the things that is common in our competitions is Eternal Blue, a exploit from like 2017, and it's pretty bad. Networking. Networking is not working. This one's chilling. Ooh. Okay, so I just turned the firewall off on this Windows machine, and it's still not receiving network traffic. Let's see. What is wrong? While I fix the demo, also my browser crashed, so I have to get it set up again. Marshall and Jess, you guys want to answer questions they have on networking? Or on the previous slides that I went over?
That works with me. Who plays red team? So pretty much anyone on the CCDC team who isn't like designated as green team or any other role.
Is anyone confused about anything that was mentioned? Green team is kind of like the people who are running the competition in a sense. Like we create the environments or send out injects, help you guys reset passwords, stuff like that. So kind of like the operations team behind the scenes. Yeah, it's confusing because different competitions will have different like colors assigned to the same roles, and like depending on which competition you're involved with, like you might hear different colors used for different roles. But in the context of CCDC, we're just operation people.
I don't know what types of fire. I believe not, as long as it doesn't cost money. I believe.
Yeah, anything that is not paid.
Unless they provide you with it.
Unless, you know, the license they give you doesn't work and then they tell you to cry about it, right? That definitely doesn't happen. It seems Evan is back. Oh.
All right. Yeah, that was very silly. But so here I have on the right side the pfSense router in front of my server 20 12 FTP server. Right here, it's chilling. If we do a netstat, we can see that it's hosting port 445, which is SMB. I don't think. I think it's dying.
Do we have any other questions before we get started? Or resume for the third time? There we go.
Okay. So maybe now it will work. But we may have secured this. I'm going to blame Tanai. Let's wait for it to start. And also, here's an example of that one-to-one natty. If I could show you the IP of the server 2012. But you can see I'm using the 172.16.90 And that's because this VM is running from a network outside of this 1790 FTP boxes network. And so the pod is currently doing one-to-one NAT. The FTP IP address is 192.168.1.120. You can see that one-to-one part is translating from 120 to 120. It's just the network portion that's changing. That's allowing us to access it. And so during the homework or during the competition, if you're trying to access something on these private networks in these pods, then instead of using that 192.168 in your browser, you're going to want to use 172.16 and then .pod number. See, it's 1790 pod, and then our third octet is 90, corresponding with the pod number. Now, let's see if it works. No. Is it the wrong one? Also, what I'm doing right now may be useful for you in the future, by the way. There we go. So you see, it's trying to do the exploit, but wait, it timed out. Why would it time out? Whoa, the IDS IPS is working, right? So look, in our block section, it's blocking that Kali VM, and it's telling you which exploits were used and which ones it detected in the network. And so there's modes. In the IDS mode, it'll only do these alerts, and it won't block that traffic, right? But since I have it in IPS mode, it's blocking it. So now, red team is like, oh, where'd the box go? You can't even ping it. And so that's like the power of the IDS IPS snort image. I'm running it in the pfSense. Very powerful tool. But also, if you misconfigure it and you like have it detect every single thing, you'll probably block your users. And so you have to be kind of thorough with what you're blocking, what you're expecting. You know, most things in networking, you have to be thorough, be careful, or else you'll end up blocking your actual users. But yeah, I think we're chilling. I'll leave that for the homework. Yeah. So if you haven't already, please fill out the attendance form so that we can email you credentials to your pods. Oh, what settings do you change to fine-tune your rules? Sorry, I can't really see the chat while I'm screen sharing, so. So to fine-tune the rules, I would go to my interface, right? And then here you can see the rules being applied to the interface. It's a lot. And so that's why typically you would run most things in a detect mode. Well, like say I only wanted to enable emerging exploits. Then you could disable all these other ones like custom, not custom, like decoder rules. These are, you know, not as dangerous as the exploit ones. So you can disable those, have it only alert or something like that. You can have it block your exploit, block your malware, block your Trojan rules. Most of the ones I have problem with are the web server rules, because sometimes clients just make kind of funky requests and they'll end up being blocked, even though they had no malicious network traffic or malicious intent in the request.
So can you import your own custom rules?
I can. You can do custom rules here. It's just the syntax is very not fun to use. So for things like this, I just pretty much use the pre-existing rules, and you kind of just have to make sure they're updated to the current rule set so you don't get like popped by a 0 day that was released in the last month. But yeah, like say I wanted, oh, this rule looks like it'll break my service. I can just remove it from that state by clicking on that. And yeah, like now green check mark, it's allowed through. Like say you only wanted to do eternal blue, you could just like, oh, my bad, I got it backwards. For competition, I didn't have to write any custom rules. I pretty much just relied on the exploit rules here, or also sometimes the Trojan malware rules. But most of the things that pop up will be in emerging exploit rules, and those are updated quite frequently, so it's nice. Thank you. So like here, yeah, this is the syntax of the detections. It's pretty much just inspecting the packet for these strings that shouldn't be in the packet. And then it can choose what detections to run on what based on like server type, like application type, port, you know, the works of networking. But yeah, I got it backwards before. If it's a green check mark, it's enabled for detection. If it's a red X, it's disabled, it's not doing anything. So say I wanted to only have these SQL rules enabled because I'm only hosting an SQL server. I can just disable all the rules. And then I swear there's a better way to filter this, but I can't find it right now. So I would just go here, click the rules I want to enable, and then it would be chilling. But yeah, a faster way you could do this is find a rule set online, uncomment the lines you want to be active, and then you would import it into the custom rules here. Yeah, I didn't go in depth into like setup of all this because that's what you guys are gonna have to do during your homework for this week, as well as kind of configuring firewall rules. But yeah, like it's a lot. It's fun. You can be very precise with these firewall rules, and it gives you a lot of options. Like say you can block by voice. You can just block voice traffic. You can just block single clients. You can invert matches. The logic is extensive and it's very useful. And most firewalls will have logic like this. And so getting practice in on the pfSense will pretty much expand into like say Palo Alto, Cisco firewalls. Yeah. Oh. My slides are closed now. I have to show you this slide because we spent way too long on this. The OSI model? Yeah, here's the OSI model. It's great. If you want to learn more about it, you should Google it, but I'm not going to go over it because it's a lot and it's not too useful in this context. But for future, in like the real world, if you know the OSI model, it's very easy to troubleshoot things. And yeah, I recommend you look it up. It's pretty interesting. Interesting if you like networking, but you can get pretty in depth into what goes on at the network level of like transactions between computers. Oh, it says no. And then, yeah, time for lab. Lab can be the homework for this week because it's pretty extensive, especially if you haven't had any experience with firewalls in the past. And so, yeah, make sure you fill out the attendance form so we can get a pod to you. And any questions? Apparently, I'm very lonely. So if you ask questions, that'd be much appreciated.